the Test Consortium. I was asked to introduce John Chabelle, my boss, for his segment of the talk. Fortunately, I got out of it when he decided not to show. Unfortunately, then I had to take his place. Then, fortunately, again, he decided to show, but now, unfortunately, I have to introduce him again. John is a computer repairman who's been elevated to the level of manager.
Fundamentally incompetent.
I like this dialogue between the podium and the audience.
Does he have a mic for the benefit of the TV?
And John will be talking today on the field service business and its relationship to what we're all here for, design for test. I guess that's good enough introduction. So,
thank you so much.
Okay. I guess most people want to hear you.
Yeah. So I'll get started. It's not clear to me whether I need my notes or not, so let's give it a try. Interestingly enough, high tech is really a problem for most of us. Can we dim the lights and focus here? You're going to need to really dim them, folks. Trust me. No problem. It gets brighter as I go on, so don't panic. You know, when we think of engineering, you know, the image we get is like Colorado Springs, the view of Pikes Peak, and all that. Engineering is really a lovely profession, and you have these lofty goals. As Steve said, I'm a computer repairman, and I have been for 15 years. I'm sort of a distant cousin of the Maytag repairman. I'm not as fat as he is. I'd like to think I'm a little brighter and better looking, but that's about it. I'm a computer repairman. And computer repair is a lot like life in a swamp. I mean, when I joined DEC, a lot of people had this little Xerox thing, you know, a little poster on their walls, and it said, when you're up to your in alligators, it's hard to remember that your original mission was to drain the swamp. And I always liked that metaphor, because service is literally that. It's a swampy job. I don't mind it, I really don't. And in fact, one of the nice things about it is you know you're going to have alligators, they're customers, and you know you're going to have swamps and they're broken machines. So just to set the tone, I live near a swamp and that's it. I took a photograph of my backyard. So to set that tenor, if I could have the next slide, what I'd like to give you is literally a view from the swamp, or a service perspective on what you think of as design for testability, and what I think of as design for diagnosis. The two have a great deal in common, a great deal, and yet I will talk about them to a degree as if they were different. It's merely conscious hyperbole, so bear with me. To begin with, you've got to remember what service is to DEC. It's a product. If you get the DEC standard price list, it's right there as a line item with a price on it. And the reason it's a product is because we make money at it. But it's more than that. Number one, it's a value attribute of our systems product. Simply put, customers don't buy hardware they can't get fixed. You wouldn't buy a car you couldn't get repaired. Secondly, it's an account control vehicle. After you buy a system, the primary person you see if you're a customer with a DEC badge is a computer repairman, not a salesman. We are the link to that customer over time. And third, and least important really, is it's an important business. We make money at it. Fiscal year 85, we will make about $1,500,000,000 gross. And in doing that, we will execute 2.5 million service calls. That's a lot of tests and diagnosis, believe me. Next slide. Now, the problem with service as a business, unlike building product, is that it's not a lot of fun. It's very complex. I could talk for an hour about why. It's very unflexible. I could talk for another hour about that. Simple example. We're prohibited by law from delivering service in India. It's that simple. We can sell stuff. We can't fix it. It's illegal. That is very inflexible. It's risky. It's risky for a variety of reasons. Think about it. Let's suppose we decide to build a product, and it's a dog. What do? We simply phase it out of production. You know all the ones you shipped? We live with them for a decade, even if we lose money. It's very dynamic for obvious reasons. And the last point most people don't understand, it's competitive. There are people out there who compete with us for service revenue. They are tough competition. They do all kinds of nasty things. In addition, a lot of customers fix their own stuff. So in case you didn't know it, DEC doesn't fix most of what it sells. We own approximately 48 to 50% of our total service market. And the rest of it is owned typically by a self-maintenance customer who wants maintainable and testable equipment whether or not we fix it, or people who compete with us in the open market, and it's ferocious competition. Whoops, if you could back up one more. Sorry. And the thing to remember about service is it's primarily dependent on product attributes. Our value added is smart human beings, and we don't have a monopoly on that. I assure you, the folks that work at IBM, we like to think we're smarter than they are, but it's only by a little bit. The pool of humanity, the gene pool, is roughly the same for them as us. If you don't put it in the product, we don't get it. And lastly, please think for a moment about self-maintenance customers. Many people only buy our machines because they can maintain them themselves without hiring to hire PhDs in EE. And a lot of those folks are very important customers. Some of them you've heard of: NSA, CIA, Air Force, Army, Navy. Yeah, they're big companies. The service product, really, what do we offer? We charge roughly $80 an hour. What do we offer that's worth that? It's really two things. One, we offer diagnosis. People think of service as swapping out a bad module. Anybody can do that. It's knowing which one. That's important. And because of that, that's the value we add. And in addition, and this is increasingly important, we provide the management of information, personnel, and material. And increasingly, I use this analog within the research community, and they understand what I'm saying. The delivery of service at a tactical level looks just like modern warfare. Believe it or not, an awful lot of the best literature to be published recently about maintainability engineering came out of the Falklands War. And the result of what we do is a lot more than repair. The way to think of it is we sort of fix stuff on the side and do diagnosis and a bunch of other stuff as our basic business. Swapping out a module takes 15, 20 seconds. And in that same sense, I'd like to leave you with a feeling that diagnosis, the thing I worry about, is more than test. Not more in the sense of better, but more in the sense of extensions thereof. And that's really the purpose of the talk. Now, what's the word diagnosis mean? I mean, I like to go to the dictionary. I literally started in a one-room schoolhouse, and about the only books we had were dictionaries and encyclopedias. So I got in the habit of reading dictionaries, believe it or not. I looked up the word. It comes from the Greek that means to distinguish or to know. Diagnosis. It means, and this is roughly what every entry in the dictionary said, in several dictionaries, identification of the nature and cause of a problem based on its symptoms, right out of the book. Important concept. In the beginning, there are symptoms, and that's where it starts. Now, let's just keep that in the back of our minds for a minute. Most people think of diagnosis in a field context like this. They say, hey, the machine runs great, you know, nothing's happening, the customer's happy, and all of a sudden, bam, it dies. Customer picks up the phone and calls DEC and says, it's broke, fix it. And we ask him a few questions like, what's broke? And he says, oh, disk drive somewhere, I'm getting bad data. Okay, based on that, we adapt a test strategy. Where's my disk diagnostic? I got it, it's on this floppy. Stick the floppy in, turn the engine, the CPU, into a tester, test the object, in this case a disk, and based on what you find, repair, replace, or adjust. Let me assure you, that is a very bad model. Not that it's incorrect, but it's way too weak. Now why? Well, to begin with, it's oversimplified. The world is a great deal richer than that now, and if anything, it's getting more richer over time. Secondly, it assumes the fault is reproducible, that whatever caused the customer to call in the first place you can do again. It assumes almost that the only way automobiles fail is you're tooting down 495 at 70 miles an hour, and all of a sudden you come to a complete stop within about 2 nanoseconds. Doesn't happen that way. And lastly, it almost, but not entirely, ignores economics. And I'd like to tell you why. First of all, why is it oversimplified? Well, think about it. Clearly, we worry about hardware faults. Of course hardware breaks. And sure, we repair or replace or whatever. But increasingly, we worry about a few more things. And these things are of increasing importance. First, we find a lot of design faults. Now, in the software world, you don't have a problem with that. Anybody here from the software side of the house? Bugs are a fact of life, right? We charge $10,000 for a PL1 compiler. When we give the customer a reel of tape that costs us $12. And we tell them, oh, by the way, that product's got bugs in it, and you'll find them, don't worry, and when you do, call us and we'll fix them and we'll bill you. Sounds funny when you say it that way, but that's a perfectly viable service. And the reason it is because software is so complicated that people assume you never get it perfect. Well, guess what? The hardware is getting so complicated we never get it perfect either. And as a consequence, this year I think we will spend $50 million installing design fixes. We have to diagnose those. And it's just like debugging software. It's just underlying the flaw happens to be some iron. Environmental disturbances. You wouldn't believe how extreme and extraordinary these can be. Simple example, trust me on this, there is something about the Sea of Tasmania that does not like DEC computers. Honest. We take, per capita machine, more environmental calls in Tasmania than any other place in the world. And we don't quite understand why. One call I refused because in order to take the call, they said the guy had to pass the insurance survival test. I said, what is that? And they said, we take him out in a helicopter, he has to parachute into the ocean, inflate the raft, get in it, and radio for help. And I said, to take a service call on an 11? And they said, yeah. So I finally said, no. But that's a true story. I was blown away by that. And that was in the Sea of Tasmania. Operational error. As the systems get more complex, the operator makes a mistake. In both cases, what do? We tell the customer something. We don't fix anything. The customer goes, it hurts when I go like that, and we tell them, don't go like that. And again, that's a valuable service. We had Brazil, out in the boonies of Brazil, guy installs a disk drive right next to a wall like that. Behind the wall is a bus bar that feeds an aluminum smelting plant. The bus bar is pumping 180,000 amps. And he wondered why his disks were dropping bits. We told him why. He paid a lot of money for that. Many, many thousands of dollars. Because we not only had to tell him why, but how you redesign, and we literally had to tell him how to reroute the power system for an aluminum smelting plant. And that's what we billed him for. I have an architect working for me. He's a serviceman. He's a computer repairman. He just happens to be an architect. He couldn't. The room was literally about 12 feet wide, and the field strength across all 12 feet was strong enough to erase the disk. Wow. And that was it. The next move out the other wall was outside, and you really don't want to put a disk outside in the jungle of Brazil. I mean, this was boonies. Believe me, that was one of the worst service calls we ever had, because we had to ship down about $40,000 worth of test instrumentation, and then the Brazilian government wouldn't let us ship it out. So we finally worked a deal. They let us ship it to Germany. So I had this stuff, went from Brazil to Germany and then back to the United States. And in the process got broke.
John?
Yeah.
You going to tell about the dog?
Oh, yes. We had one call. This is in slightly bad taste. Forgive me. I have no class. We had one architect who had a word processor, and about every 4 weeks he'd call in because his floppy was malfunctioning. You swap the floppy out, right? It's a whole thing, right? You can't fix it. We don't know what's wrong with it. It just can't read right. So about the 4th time through, we got a call, and the guy said, gee, you know, I looked at it, and it seems to be slightly corroded. Okay, I have a corrosion engineer. I really do. Jim Michnewicz. He's superb. And Jim got it. We sent it through. We sent it through X-ray spectroscopy. We did atomic absorption spectra. What we found was dog urine. The guy's dog didn't like the machine, and every now and then at night he'd come by and lift his leg, and the dog was of a height that just hit the slot that you put the floppy in. We spent about 10 grand finding that problem. And naturally, what did we do? We'd inform the customer. Shoot your dog.
To build a customer.
Yes. And lastly, a performance deficiency. When you put a big system together, one of the things a customer will call you and he says, you know, it don't go fast enough. And he expects us to fix that. Well, how do we do it? We evaluate his design and we tell him you've got a bottleneck. Take a look at your paging rates. You need more memory. And he goes, gee, thanks. I'll call the salesman. Fantastic. That's a service. You don't think of it that way, but it really is. Sorry to belabor the point. Now, is it reproducible? Well, there's two problems with reproducibility. First, it assumes the equipment's available. You walk on the site, you say, what's broke? He goes, that. And of course, the customer turns it over to you. Well, the way we used to do that, you take an 1170 system worth $500,000 and you go in, you say, what's broke? The line printer. Okay, give me the system. I'll load the diagnostic. I'll test the line printer. What always amazed me is we had to take an 1170, turn it into a rather bad piece of test equipment, and then fix the line printer. Now that customer on the open market would sell time on that machine for $200 an hour. And they were always kind enough to give us the machine for free. And I always wondered about that, because if I had a contract and you took my CPU away to fix a line printer, I'd bill you for rental on the CPU. They never did, naturally, and we have little fine print in our contracts that preclude that. But think about it. I mean, who would ever really consciously design a line printer tester that was yay by yay, cost $100,000, and was meant to run PDP-11 code? But that's what we did. Secondly, it assumes a stuck-at fault. There's a joke, Billy Carter joke. When Jimmy Carter was our president, Billy Carter was asked, Billy, what's the greatest invention of the 20th century? Billy thought for a while and said, a thermos bottle. Billy, how could a thermos bottle be the greatest invention of the 20th century? And Billy said, well, it keeps hot stuff hot, keeps the cold stuff cold. So what's so great about that? He said, it's not that. He said, it's getting the glass to know which to do. Same problem. Who the hell told the transistors they were supposed to stick at? I know the laws of thermodynamics, I know most chemistry, I really did go to school. And I've never found a law that says transistors have to stick at anything. Think about it. It ain't in the textbooks. It's a good model, perfectly good for developing test vectors, etc. But again, nobody told the electrons. Now the problem, really, the economics is, in the end you're left with 5 to 10% of the problems that just don't fit the curve. And they cost a lot of money. I'll get to that in just a moment. Second, equipment and system time is not free. It costs somebody money, either us or the customer. In either case, the customer ends up paying, and they don't like that. Customers don't part with their money easily. And lastly, if you look at service labor cost versus logic cost is going, pfft. Service cost goes, minimum cost out the door in Germany for a call is about $300. I mean, we don't get in our car for less than that. And I think most of those guys drive Mercedes, although I'm told that really isn't the case. So given that, let's take a look at repair times. Because again, this is what diagnosis is. This isn't repair time, it's diagnose time. The repair takes 30 seconds. Maybe adjusting a disk head might take a while, but most repairs are trivial. This is diagnose time. Typical mode, our common repair times are about an hour, of which about half is test time. Our typical means are in the 2 to 3 range, where the test time is on the order of 1.5 hours or so. And then you get this tail out to the 8 to 10 to 12 hour range. Very small percentage. But let's look at the cost distribution. Where's the money go? If you plot this function, which is a log normal function, times the constant cost per hour, you get a product function. If you plot that, you get this funny curve. Turns out most of your money is spent, here's your mean repair time right here. Most of your money is spent on calls longer than that. Very small minority, 5 to maybe 20%. We call it the tail of the dragon phenomenon. This is where the money goes, not here. This is easy. Let's take another look at that. This is a real machine. Relatively early in its life, we actually tracked it. It was a fairly testable machine in the common parlance of its time. It was not a terribly diagnosable machine, however. So if you look at the repair time distribution, you find most of the calls, hour, maybe 2 to 3 to 4, but pretty pocketed in here. And then we had maybe 8% of the calls took longer than 16 hours.
What machine's that, John?
You remember it. It was called the KL10. Next slide. Now, if you plot where the money goes, this is the 50th percentile point. That is, half of our money was spent fixing calls that took less than 14 hours, and half were spent on calls that took longer than 14 hours.
This isn't counting the hardware that was replaced.
That includes everything.
Everything, okay.
So next slide. Just to tell you, the problem's out in the tail. Now let's look at some more contemporary equipment in less detail, because we have such a large population out there, it's hard to track real close detail on these machines. 20% of our 780 calls consume 63% of our total resources, labor and material. That's $17.7 million out of a potential expense of $28 million. Spent on that top 20%. 18% of our 750 calls consume 40% of our total resources. Let's look at it another way. 70%, actually more than 70% of our 780 and 750 calls consume no material. The vast majority of service calls on contemporary VAXs, CPU kernels, consume no material. Why? 2 reasons. One, you go out there and you can't figure out which module to swap, so you give up and say, hey, call me if it does it again, right? You've seen that. Gee, it did it again. The French have a beautiful expression for that. It loosely translates into the duck is still alive. I don't know quite where it comes from, but I always remember that. The other reason is that, remember what I told you earlier, a lot of our calls aren't traditional hardware repair. There's something else, but they still involve diagnosis. This is what we're beginning to see. Systems generate symptoms all the time. In fact, to a close approximation, a large 780 always has something in it that's broken. Your job is merely to discover it. Every now and then, one of those problems will bubble up to the visible surface to a point where a customer says, I'm mad as hell and I won't stake it anymore, you know? Picks up the phone and calls DEC. What we then want to do as much as possible is get as much state information about what caused that symptom. And from there, what we'd love is to be able to say, you know, the only thing that could give you that symptom is this field replaceable unit, or other service action. I.e., you know, that symptom could only be a design flaw, or that symptom could only be the architect's dog. That's pushing it a bit, but it'd be nice. Now, sometimes that doesn't work so clearly. We're going to test, too. Eventually, if it's a hardware fault, you identify the fault to a field replaceable unit. You take this incredibly complex module. I mean, again, at the risk of sounding a little funny, on a 780, we don't really fix anything. We swap out a printed circuit module and put in a good one. The only thing that's happened is DEC is now the proud owner of a busted module. I mean, nothing's been really fixed except the customer. So now we've got to take this module back to a repair depot somewhere in the world, test that, and repair it to a component. So this is a fairly rich problem set. And the point that I would emphasize is that this mapping, the ability to identify a large field replaceable unit based on symptom and state, is clearly nice, because if you can do that, you don't have to test anything to get to the FRU. And that's a big help, because once we get that big FRU out, we still have this enormous problem of testing that too. Yes?
Do you include a remote diagnosis exercise as a visit? That is, I mean, how often is it the case that that customer has a problem, calls up, remote diagnosis center, exercises his machine, and if they can't find anything, presumably...
We don't dispatch somebody, but it's still a call.
But it's still a call.
Oh, yeah. And in the end, the customer will call back most of the time. That's why we're investing so heavily in remote diagnosis, because the one thing it saves you is wasted trips.
Right.
I mean, it costs, you know, it's $60 an hour whether we're driving a car or repairing a computer. So, what are we trying to promulgate as a strategy? Well, we surround some words around it so we have a banner to march under. Don't take the words too seriously. We call it symptom-directed diagnosis, and it's our basic posture. That is, wherever possible, if you have a hardware fault, migrate the burden of field replaceable unit identification to error detection logic, state capture facilities, and multiple state analysis tools. I'll talk about those in just a moment. It's not that simple. There are really two cases. The first case is I get a symptom and I get some state, and by looking at them I say, you know, that could only be that module. And we call that single event correlation. Simply says, look, conceptually I have a little flag on the back of every FRU, or a little LED, and when it lights, that's the one I pull out. It turns out for most contemporary large systems, the problem set is much broader than that. So what you want to be able to do is collect information about many symptoms. I mean, if you have a system crash once a week, the customer isn't going to call for service. He really isn't. He's just going to, oh, it did it again. If it gets down to once a day, he's going to call. Well, if you're smart, what you've done is kept a record of the machine state on every one of those crashes. You can then go back and hopefully analyze what you saw. Now, the way that's done, in effect, is to basically do the logical equivalent of a Venn diagram. You look at all the symptoms, try to correlate them, and in the end you say, you know, the only FRU that could give you that common set is this one. Now, it turns out this is a pretty important concept, more important than we originally thought. So, with that, let me give you a few heuristics. I mean, I could talk about how you do this for a long time, but I'm not all that good at it, so I'll give you some heuristic, rules of thumb, things to think about. First is the 11th commandment. People really, a couple of my friends are Israelis, and we occasionally talk about the Bible in Hebrew because I can't read Hebrew. But there is sort of a standing joke in Israel that, translated into Dek Ish, goes as follows. When Moses first went up Mount Sinai, he came back down with 300 commandments. You know, I mean, it was a huge load of slate, all carved, you know. That was Rev 1. And he negotiated with the Israelites and went back up, and, you know, they had several woods meetings over time, and eventually they got it down to 10. And Moses was actually a field service manager in his first life, you know, in Egypt. He was a repairman, much like myself. And he said, you know, we got some good news and some bad news. The good news for you field service guys is that drinking is no longer a sin. He said the bad news for you field service guys is adultery still is. But this was a commandment that got dropped too. Design assuming that faults aren't reproducible. Now, given that, you're left with a problem, and that is error detection design. And that's a problem in physical and logical partitioning. It's not enough to detect errors. You have to do it conscious of what the physical object looks like. I only need to know which module to pull. I don't need to know which half of the module's bad. Secondly, what's the failure probability? If you put on error checking, you ought to have some sense of how often that error is likely to occur. We don't do that normally. We think of errors as being somehow equiprobable. Design integration. How do you integrate error checking into the design? As commonly done, it often impacts performance. Slows the machine down. There's no law that says it has to. There are clever ways of not doing that, but all too often we just think, oh, we've got to detect errors. Well, that means we've got to slow the clock down. That means we've got to trap the error, take an interrupt, etc., etc., etc. And my immediate response is, to light a lousy LED on the board? Do you really need all that? And lastly, cost and performance impact. Clearly there is a cost and performance impact. Hopefully it's zero. But you've got to know what it is before you make good decisions. But again, error detection design probably is the single design for diagnosis discipline, much like design for observability and controllability is the design for testability discipline. Secondly, you've got to capture state. The typical software support person would be lost without a crash dump. We need the same thing. The only thing that crashed in our case was hardware, but we still need to know the machine state. It's often an afterthought. You collect all the bits and then getting them out of the system is very difficult. It shouldn't be. It must be integrated. IBM's level sensitive scan is a fascinating study in this because the test community thinks of level sensitive scan as a controllability visibility vehicle. IBM Field Service sees it as a way to get the crash dump out of the machine. You get an error, they halt the clock, shift the registers out, store them, start the clock up, and away you go. Hitachi happens to use a state silo. Also a very nice idea. Hitachi says, look, I don't need all the bits, but I need to watch the bits over time like a logic analyzer. So instead of having this long horizontal crash, they have a narrower, time-deep crash dump. But again, it's a crash dump of hardware. No great shakes. The nice thing about state capture is that it often doesn't impact performance. And secondly, it often increases system availability. IBM uses level-sensitive scan to amplify their instruction retry capability. You get a parity error. Shift out the registers, look at the source register, look at the destination. If the source is correct and the destination is bad, shift in the right destination, shove it back in, start the clock up. If you don't get another error, it was intermittent and the system keeps running. Rather clever, those folks. Multiple event correlation. One of the things we learned, partly as a result of digging into artificial intelligence, is how expert diagnosticians work. The initial research was done with medical doctors. How does a doctor diagnose you? The first thing, I mean, can you imagine showing up at your doctor and you say, Doc, I got a problem, and he goes, okay, fine, I'll put you in the hospital, we'll do a blood test, GI series, x-rays, the whole bit. I mean, it doesn't work that way. He asks you a few questions first, you know, like how you feeling, what's wrong, has it been with you a while, have you had this before? How about a family history? Does it run in your family? That's multiple event correlation. And as it turns out, the folks who did that kind of expert system work in the medical world happen to find doing the same thing for computers fascinating. So for mere money, they're helping us out here. And as it turns out, it's really our primary tool strategy. It works surprisingly well. It works as well, almost, as the medical profession does, which isn't bad. And unlike humans, you know, actually you can think of this more as computer veterinary than computer medicine. And it is amenable to AI approaches.
Do you have a working project?
We have many.
Okay.
We have an AI tool that takes the, most of them are prototypes, but they work so well we actually use them in production. We have one that diagnoses TU-78 tape faults, and we have yet to find a flaw in it. We have one that does consultative support for troubleshooting DECnet networks, and we are building a crash dump analyzer that goes through, looks at a crash dump, tells you what else to look for, and tells you what it thinks is wrong.
Could we get together after this is over?
Sure. Yeah, and in fact, I am not the most knowledgeable. The manager in my group that heads that function is Neil Pundit. He's in this building up 2 floors. He's right near where Sam Fuller used to sit, but on the 3rd floor. And lastly, it turns out if you can count on having multiple symptoms, you can minimize your detection and capture requirements. And it turns out you can almost always count on having multiple symptoms, because initially the faults tend to be very infrequent. And as a consequence, the customer is going to live through 3 or 4 system crashes or unrecoverable read errors or something before he calls you. About the only time we get a call is when you really get a true stuck-at fault. And those do happen all the time, but those are easy. Or the thing goes up in smoke. And that doesn't happen all that infrequently either. You get a call, a customer says, hey, it's on fire. You tell them, turn it off. I could tell you a funny story about that, but I won't. Catch me offline. It's cute. Oh, okay. Hey, what the... I'm always conscious of... There's a lot of videotapes of me somewhere in DEC, and someday somebody's going to put them all together, and I'm going to be in deep trouble. But until they do. Yeah, what happened when we first instigated remote diagnosis, we tried to come up with processes and procedures, you know? And so the typical model, much like I showed you, was machine runs, machine breaks, you run, test, and fix. So we gave people who were call handlers the script. You know, say, what's wrong? Okay, do this, do that. So the customer calls up and says, I got this disk drive problem. Oh, okay. Fine. If you got a diagnostic pack on site, yeah, but you don't understand. I got a disk drive problem. Okay. You got the diagnostic pack on site? Yeah. Okay, take the diagnostic pack and mount it on the drive, and we'll run diagnostics. No, you don't understand. I got a disk drive problem. Okay, what's your problem? It's on fire. You know, you don't think like that. We never think that we have to diagnose equipment that's on fire, and occasionally you do. It's pretty rare. We had, I kid you not, some customer, who will go unnamed, put, I think, 17 11780 CPUs in a tent north of the Arctic Circle in faraway Lapland. And the tent developed its own climate, and it rained inside the tent. We had to do corrosive analysis on every single 780 to convince the customer that in fact the VAX 780 spec specifically meant that the machine was not meant to survive rain. And we had to do that for the insurance company. And again, this multiple event idea is very important. We're only beginning to understand how you do it, how you mobilize it, and how important it is. What I'll tell you is we have done successful prototypes that work and are used on a daily basis, and so far I'm impressed. And for what it's worth, the medical profession's experience with AI correlation has been similar. It doesn't do everything, it's not a panacea, but it works pretty well. What are we doing? We being customer services mostly, but there are other contributors clearly, many of whom are part of the design for test community. We're doing basic research. Without going into detail, the research we're doing at MIT is basically computer biology. It's attempting to begin to develop expert diagnostician capability a la computer medicine based on the underlying science, which in medicine is biology and which in computers are the laws of physics, Maxwell's equations, thermodynamics, and the like. And I literally think of it as computer biological medicine. We have a project at CMU that, again, using a medical analogy, and this sounds funny, is more like computer psychiatry. Both avenues of research are proceeding quite well. Again, the reason it is, psychiatry is not a science based on first biological principles. It's based on observation, inference, and behavioral extrapolation. And the CMU research is in that ilk. It says, look, I know nothing about what's inside the box. All I know is what it's supposed to do. I mean, I know what a human's supposed to, I know a sane human being when I see one. So my problem is when I see an insane human to partition the disease into schizophrenia, paranoia, cerebellum damage, etc. Knowledge engineering. We are doing expert, that is as in AI-based expert systems, diagnosis. The TAP program is a TU-78 diagnostic tool. CDX is a crash dump analyzer, and NTC is a network troubleshooting consultant. It's a human amplifier. It doesn't solve the problem, but it helps you out a lot. We're doing error log correlation primarily in a program we call SPEAR. That is an operational tool. It's deployed today. Version 2 will go out in Q4. And lastly, we're struggling trying to understand the design techniques and modeling tools. The problem here is we're behind the curve in the industry. IBM is better at this than we are. Univac's better at this than we are. Nippon Electric, Hitachi, Fujitsu, etc. Stratus Computer down the road in Marlboro is better at this than we are. Now, just as an aside, you don't need to go back in the slide, I brought some handouts, just some articles, one on the IBM 3081 and a couple of others that are relevant in this space. And if you care to take one to read, please do. They're interesting reading. They're a little heavy, but don't take them too seriously. In particular, I would stress the one on the ED-FI mechanism in the IBM 4381. IBM calls what we call symptom-directed diagnosis, error detection / fault isolation. Same concept. Their tools are very nice. And I gather that, in fact, I think Dick Bevan left, but the Aquarius team is pursuing a similar strategy. Now, what about testability? It's equally important. We've got to do both. Because we really do get real stuck-ats. They happen all the time. Secondly, we just as soon have the checks built in. I don't want to have to turn the CPU into a printer tester. Most importantly, most of the time we run a diagnostic program, it runs to completion successfully. That's because you may not have to run a diagnostic program to test the thing, but you always have to verify the fix. And hopefully you fixed it, so you're going to run from start to finish after repair. And lastly, remember, we've got to fix the FRU, and that's getting to be really tough, as those of you in module test know. Some trade-offs, quick comments. One, you have to trade off the probability of fault recreation versus the probability of doing correct analysis. And I guess I would say, trust me in this, over time your probability of doing good analysis grows, partly because of the research, partly because increasingly the CPU is one module, the disk controller is one module. I mean, how can you partition it more than that? There's also a trade-off between diagnosability and testability and reliability. It's often a complex one. The common thinking is that if you add stuff to improve test, you add more to the board, and hence you decrease reliability because you have more components. Again, sort of a trust me here, most of the time that ain't the way it works. With IBM's level-sensitive scan, they've increased system reliability, and they added a lot of logic. Product cost cost versus service cost. Simple answer here. Our goal is usually the lowest possible cost to the customer because that's what he cares about. Whether it comes in through the service avenue or the sales avenue doesn't matter. It all comes in through Jack Shields and the customer sees it as real money. Market value versus product cost. What is the value of a highly maintainable and testable product? Well, part of the value relates to service, clearly. But what about the guy who has to do self-maintenance? That enters into his purchase decision, so clearly it's a value or quality issue. We don't know how to do those well. Nobody does. But you got to think about it, because if your competition does it better than you do, you still lose the sale. Key point here. In almost all cases where you have to do a trade-off, models do exist to evaluate alternatives. You notice I didn't say good models, I said models. It's a lot better than nothing. Secondly, there are a few rules of thumb that work okay. For a given problem, you can often decide, given you have a binary decision, you either go left or right, you can often make a good first pass just based on some common sense and a few rules of thumb. Good rule of thumb, if we have to leave the office to take a call, it's $300. And lastly, a little plead with my counterparts in engineering. The usual pushback I get is we never get enough data from the field. You're never going to have enough data. It's not going to happen. If you wait until you have enough data, it's too late. Your competition's already ahead of you. The competition doesn't have enough data either. I mean, I hire analysts from IBM. They tell me the same thing. The engineers never have enough data. And that isn't the problem. Some examples. What's it worth if we could reduce the mean time to repair of DEC by 1 minute next year? Well, that's 2.5 million calls at $1 a call, because it's $1 a minute. That's $2.5 million that trickles right through the bottom line. That's 3 cents in earnings per share per year. That's non-trivial. What if we could save 10 minutes off the repair time, which is, again, mostly diagnosed time of a 780? Well, at about $12.50 a call for 10 minutes, 780s are a little more than $1 a minute, 5 calls per year, that's $1,500,000, which translates, if you work through all the accounting mechanism, to $300 in transfer cost. That is, if by investing $300 per unit in transfer cost, we cut mean time to repair by 10 minutes on a 780, that's a wash. It's a break even for the company, but guess what? Customers are happier. So what am I pleading for? I'm pleading that you think about design for test and design for diagnosis. Not as distinct entities, but rather as a continuum of related technologies, tools, and techniques with one common goal, and the goal is survival. I mean, it's really a jungle out there. I mean, my world's a swamp. If you're in sales, it's a jungle. And what's nice about working for DEC is our customers really do want us to succeed, if for no other reason than we have so many self-maintenance customers. But remember, our competition doesn't. So while I really like the engineering view of geography, a view from the Pikes Peak and the mountains and the snow and blue sky, and I really don't mind the view from the swamp, way down the road from me in Stowe, there's another view that I just thought if you could hit the button, and that's the view from the dump. And if you could hit the next slide, yep, there it is, the Stowe Sanitary Landfill. And I guess in closing, all I'd say is, look, you understand the problem. You're never going to have enough data or information to make an absolutely correct, sure decision. I'll help you all I can, so will my people, but you'll never know enough. You got to take some risk. I'm left with the sense, I don't know how many people watch Hill Street Blues, but they have the new sergeant, and every episode starts out the same thing. He gives the briefing and says, and let's go out there and do it to them before they do it to us. It's really that simple. Thank you for your time and kind attention. I'll be happy to handle any questions you might have. Yes?
Do you have a copy of this entire presentation?
In a word, yes, in the sense that I forwarded the copy of the slides, and I believe they're in the they're in the notebook.
Wait a second, the copy that we have in the notebook, John, is not exactly what you presented.
Okay.
How about if you give me your
Sure.
overheads and we'll make some more copies.
Okay. I can make duplicates of the...
Slides, I want the overheads. I'm not going to make copies from the slides.
Okay. If you want, I can have copies made of the 35 millimeter too. Because I don't have the swamp on transparency, you know.
Why don't we work that off?
Sure, whatever you'd like. Tell me what you need. Yes, you had a question in the middle. I'm sorry I missed you. It just slipped my mind.
Well, this afternoon at lunchtime, we were told that Tech isn't making any money on hardware. That's a non-profit business.
No, that's not true.
That's what we are told anyway.
Okay.
And the only money we are making is on service. Now,
Okay.
if we give you good machines, you won't have any money to make it.
Is the tape on? If the tape's on, I can answer that one way. If it's on, let me give you an honest answer, but one that is couched in sufficient verbiage so that it won't incriminate me. As you might guess, recently, the service arm of the corporation has brought in more contribution per dollar than has the hardware arm. That isn't a matter of policy. We happen to be in a very competitive hardware position right now. We weren't some years ago. We hope not to be in the future. To a degree, I don't care. It's all money. I don't care how it comes in. I mean, I'm going to make up a T-shirt that says, "Let's help put John kids through college." What I look at is I look at the price of the stock in the morning. I just don't care where the money comes in from. I really don't. And second, the problem is people have this sense that, gee, what if we did really good and put you guys out of business? I'd be the first person to congratulate you because I'd know about it first, and I'm sure my vice presidents would be right behind me thanking you. Because in the end, the way we win is to sell machines. But we don't beat the Japanese by out-servicing them, believe me. Okay? So know who the enemy is, and the enemy ain't Sorbus, it ain't self-maintenance customers, it's the people who sell computers. For the time being, we're happy to contribute profit. Over time, put me out of a job. Because really, 10 years from now, I'd like to have a respectable career. I thought about going into politics, in fact. Yes?
Do you know what percentage of IBM has self-maintenance customers?
Very small number.
Do you understand why the ratio is different between that kind
Oh, yes. First of all, there's several answers. Let me give you a couple simple-minded ones. First of all, the markets that need to do self-maintenance, IBM chooses to avoid. They literally try to avoid them. They don't like putting 370s on oil drilling towers in the Sea of Tasmania.
Is that true, since I believe that you...
Now that is starting to change just recently through like their VAR program and their PCs and like that. So at the small end of the spectrum, Series 1, System 38s, etc., they're starting to see that phenomenon.
What about the government?
The government.
They're one of the largest IBM customers, right?
It turns out the government has more DEC and more UNIVAC than IBM. By count, it's DEC. I think by total equivalent service revenue, I believe UNIVAC has a slight edge in the government, but I'm not sure of that. They used to about 4 years ago.
Revenue and the Census Bureau. So.
Yeah. Yeah, and I know they have a lot of STC tape drives. Lots. Social Security Administration in particular, plus the government buys a lot of Amdol. They consciously spread the wealth around. Oh, the other answer. IBM prices FRUs sky high because they have very few self-maintenance customers. Most of their competition are maintenance companies. So in our case, if we price FRUs sky high, we hurt the guy who has to do his own maintenance, the universities, NSA, India, whatever. IBM doesn't have problems with self-maintenance customers because they're mostly banks who don't have a lot of technical folks hanging around, so they price the FRUs. We bought a System 38 or leased it. Small machine, roughly 11750 class machine. The CPU FRU, which is a little module, list price, because we have a full-time IBM salesman, or at least we used to. I don't know if you know that. Very nice guy. In fact, he just retired. We got a new one, and he was close enough to retirement, so he was incredibly candid. He'd tell you anything. He didn't care. And we said, hey, we'd like to maintain it ourselves, but it's on lease. Is that okay? And he said, sure, for you, anything. We said, okay, should we buy some spares? And he said, yeah, it'd be a good idea. Okay, I'll send you the price list. We got the price list. This one lousy little spare module was $30,000 list. So clearly, you don't go into self-maintenance with IBM. Yes?
You pleaded for design for diagnosis?
Yep.
Yet I just read here in one of the handouts that Scan Design obsoletes diagnostics.
No. Scan design is simply, remember, what is design for test and diagnosis? It's the ability to control stimulus, the ability to set state, the ability to retrieve state, and the ability to observe output. The nice thing about level-sensitive scan is it is a facilitator for all four. From a diagnosis vantage point, what I want to do is see output and state. I don't care about controlling state or controlling input. And level-sensitive scan is just very versatile. There are other techniques. It just happens to be a very simple technique that is versatile. Now the price you pay is it's expensive. Again, it's a trade-off. It's an economic decision.
I'd like to follow up too. I think what we're saying is that scan design has the ability that you can use automatic test pattern generation to find the local hard faults and this kind of
Yeah.
and reduce the amount of manpower that has to go into normal diagnostic programs.
Yes. Oh, that's absolutely true. I'm sorry if I misunderstood your question.
Reduce the amount that goes into diagnostic programs.
Yep.
All right. But we're talking about something different relative to diagnosis. Diagnosis is saying from this symptom, can I deduce what's wrong?
Yep.
Okay, as opposed to running a test to deduce what's wrong.
Yeah, we have to do both. Again, remember, give you an example. One of my personal frustrations, so let me bitch a little. I sit in a meeting and somebody says, we got 95% coverage. And I sort of feel like, I can't tell a customer that because he expects us to fix 100% of everything. Can you imagine going to a customer and saying, look, hey, that's 1 out of 20. We don't fix that one. I mean, that doesn't work. I don't care what your number is. We got, you know, you wouldn't accept that in an automobile. You know, driving to the mobile station and say, hey, you know, it's sort of hiccuping and I'm getting poor gas mileage. And the guy says, you know, well, this is your 20th visit. Sorry, don't fix that one. Customers don't tolerate that. So I got to fix it all. Not me personally, but I got to worry about it all. Customers just don't think like we do. They're not engineers. They depend on their output. I mean, imagine how you'd feel if your paycheck didn't arrive. That's printed on a DEC machine. Said another way, would you, if we built aircraft, would you fly us? I kid you not, one of the research areas that CMU is pursuing is how reliable does a computer that flies an airplane have to be? Because in the end it will fail. And on modern designs, for example the new X-29 that flew, if the computer fails, the pilot dies. 1-for-1 correlation. If the system crashes, he dies. The mean interval between absolute loss of control, I mean unrecoverable human pilot error, is something under what, a 16th of a second? You have roughly your maximum outage for the computer system is like a 16th of a second. And within about a second after that you go into a completely uncontrollable spin that can't be recovered manually.
This is for passenger aircraft.
Yeah, and this is for passenger aircraft. The model we were working is, what is the mean time between the loss of 600 lives due to computer failure? And there is an answer, because in the end we will have computers that fly aircraft, and the aircraft will be such that if the machine fails, the plane will crash. It's no different than having an aircraft with one engine and its wings fall off. Wings do fall off. There is a mean time between wing fall off. It's very high, but it happens. The only difference is if it's a computer, people fear it. You know, if wings fall off, they say, oh, mechanic error or something or other. If the computer fails, it's, oh, those damn computers. You know, they're taking over. 1984 killed me. But again, it's something to think about. Fortunately, to my knowledge, we haven't killed anybody. But there have been deaths due to computers. People on EKG machines being monitored by computers. They've had ground loop problems. In fact, there's a recent article about microshock on the operating table and the fact that they keep wheeling in more instrumentation into the operating room, and they're starting to find that it's killing people. It injects little microshocks due to the cumulative ground loop effects. So I just assume one of those things they wheel in not be something with my name on it. It is a real problem. Okay, again, thank you very much. Have a good day.